Welcome to this audiovisual presentation of my public access article that is published on the CHAOS website called A Redemption Song for Statistical Significance. I wrote this paper in opposition to bans on statistical significance that were declared by several journal editors and scholars, but remains a topic of ongoing discussion and debate within the scientific community, as evident by a Google search. In this paper, I use sampling distribution of means, effect sizes, and p-values to show that banishment of statistical significance is deleterious for scientific research with small sample sizes. In the paper, I guaranteed that my results can be reproduced and replicated. In this video, I demonstrate how that is achieved with free online SaaS software. First, go to the figshare.com website and enter my last name, Komarov, in the browser, and that will bring you to the SAS files that I created, as well as the data sets that are all used to reproduce the results in my paper. Next, you will need to create a free account at SAS Institute in order to gain access to their free SAS on demand for academic software. Here you can upload the files and run my programs. So let's start with simulating a true null hypothesis. So bring up the file sim true null and then create a folder, call it true null, which I've done, and it appears on the hard drive on the SAS server, which is in North Carolina, but that doesn't matter. This is an internet-driven software. So I have a folder called True Null, and now I'm going to create some data sets. In fact, I'm going to create 1,000 of them. Okay, each data set is going to have a sample size of 5 per group. The population mean is 50. The population standard deviation is 25, and I'm going to run 1,000 samples. This program, this part of the program will create 2 groups. In other words, the first 5 observations will be drawn from the population with a mean of 50 and standard deviation of 25. The second set of 5 observations will be drawn from the same population with the same mean of 50 and standard deviation of 25. Then these data will be subjected to a t-test, and I will be using alpha is equal to 0.05 as my level of statistical significance. I'm testing a true null hypothesis that the population means, the difference in population means, is equal to 0. This null hypothesis is true because both groups were drawn from the same population with a mean of 50. So 50 minus 50 is equal to 0. That's a true null hypothesis, and I'm using a two-sided t-test. The data then is extracted from the output, and the calculations are stored in a new data set called T, with this symbol to mean that it's the sample size, so it's T5 that's going to be stored. And incidentally, for each run, for each sample, I'm computing the effect size, which is known as Cones D, and that's the difference in means divided by the common standard deviation. All right, so let's take a look at this folder true null. It's empty right now, and as I run this program, it will show that I have now a new data set with 1,000 p-values, 1,000 effect sizes, 1,000 difference in means, etc. So you hit the running icon here, and it takes a few seconds, and you have the first data set appears, and here it is T5. So now you go back and first check the log, make sure that the program ran as you expect, and SAS will issue a warning or an error message in red highlight. And here I just see blue and black print, which is fine. So now you can go back, and I used 15. So you can use that sample size. And then everything else remains the same. It's just click on the running icon, and now take a look at this folder. It will now pop in with T15 as the data set, and so forth. Now for the null hypothesis, you switch to another file called sim_false_null. And here everything is the same as with the true null hypothesis, except to when you get to this point. Here, I'm adding 20 points to the first group, which I call the experimental group. And that means that every observation in that group has had 20 added to it, which also means that the population mean is now going to be 70 and not 50. So the difference in means is going to be 70 minus 50, which is 20 points. And this is going to be divided by the standard deviation in the population, the common pooled standard deviation. And now I have a large population effect size of 0.80, which I have induced in the data. And I'm going to do this 1,000 times because I'm going to be doing 1,000 t-tests. And the run is the same, except you need a new directory. You have to create a new folder, call it false null, which I have created before this run. Here is false null. And so the data is going to be stored under this folder, in this folder. And we click the running icon, and it takes a few seconds. And now you have false null, and here's the first data set. Then you can go ahead and switch the sample size. And you don't have to change anything else. And you run it again, and now you'll have another data set, which will be F15, and so forth. So as you change the sample size, that number represents the sample size for each group. And you can create whatever sample size you like, but if you want to stay with what I did, then you'll be creating 8 sample sizes. Now, let's move on to reproducing the results in my paper. For that, you need the file called analyze true false null. You need to create a folder, call it repository, which I've created on the hard drive here. So this folder contains the files that you downloaded from the fixshare.com website, as well as the programs. I'm going to be bringing those data sets in from the hard drive into working memory and combining them. Appending them is a fancy term for that, and running summary statistics and running the histograms and doing some data analysis, post-processing. So to do this, you would simply, again, click on the running icon. And first you check the log, make sure that the program ran as you expect. SAS would issue error warning messages in red. I see no red here, only black and blue print. So everything worked as expected. And now we can move on to the results. And the first result you see is the table. So let me bring up the table in the paper. Yeah, these data were reformatted to look at this way, but all these data then are populating this table. So let me explain what the table is showing you. Here you have theoretical sampling distributions. The population mean is equal to 50, and the sigma, standard deviation, is equal to 25. Now, the sampling distribution is going to have a different standard deviation. It's computed as sigma divided by the square root of n, and n being the sample size. So with 5, square root of 5, and divide 25 by the square root of 5, it'll be 11.18. And as the sample size increases, the standard error or the standard deviation of the sampling distribution gets narrower. It collapses onto the population value. And what does the population mean? Well, in this case, the population mean is 50, and in statistical theory, the grand mean of the sampling distribution also must be 50. It's equal. And that is a very useful feature, which I won't discuss from the theoretical perspective, but I will try to approximate with empirical data to see if it's true or not. Okay, so the first group we can look at is the experimental group, and the mean here are close to 50, and as the sample size increases, you have the grand mean being a much better estimate of the population mean, which is indeed 50. It is 50. The standard deviation of the sampling distribution should be similar to the standard error that is derived theoretically. And what you see are some close matches. And as the sample size increases, the standard deviation of the empirical sampling distribution also becomes narrower. And in fact, it's a good close approximation to what you should expect in theory. And this is also true for the control group, and you can see the data here as well as the data here. Now, the more interesting piece for this paper was the theoretical sampling distribution of the mean differences and the empirical sampling distribution of the mean differences. And so the theoretical mean differences, the difference between the two populations is zero, because this is a true null hypothesis. And I showed you how the data were sampled from basically the same population. Not even basically, it was the same population. So the difference in means has to be zero, theoretically. And the standard error of this theoretical difference in means can be computed with this formula, and it produces these values. Now let's see what the empirical distribution of the difference in means looks like. Well, they're not exactly zero, but as sample size increases, the grand mean is close approximation to what you would expect in theory. And the standard errors, in the case empirically, it's the standard deviation. These two are good approximations to what is predicted in theory. You see 1.18 to 1.12 at a sample size of 1,000. Now, it may be difficult to grasp exactly what these numbers represent without looking at a picture. So let's take a look at the histogram for the sampling distributions. And here we have the histogram for n is equal to 5 per group. I show 1,000 replications or 1,000 samples. The mean is 0.42, which I have in the table, and the standard deviation is 15.86, which is an approximation of the theoretical standard error. However, this is an empirical sampling distribution, so it's close. But the number here, 1586, also indicates that there is a wide spread, a wide dispersion in these means. And in fact, you can see that the minimum value, let's say it's negative 50, and the positive value, we'll round it to 64. So it's the means, the difference in means anywhere between negative 50 to 64. That's a wide range. But if we increase the sample size to, let's say, 30, or let's increase it to 100, the minimum and maximum values change. The data, the standard deviation becomes smaller, and the estimates become better estimates of the true mean difference, which is zero. And you see this particularly with the sample size of 1,000, you have a difference, well, a range from -4 to, let's say, +4. Now that's much different from the sample size with n is equal to 5 per group, where the minimum was negative 50 and the maximum was 64. Now it's negative 4 and positive 4. So it's a phenomenon of sample size. The sample size increases, the dispersion, the theoretical dispersion, as well as the empirical one, which follows theory, indicates that estimates of population values are improving. Now, let's see if this is also happening with p-values, which is of most importance for this paper. See what the p-values are doing. So we'll take a look at the p-value distributions. So each t-test produced a p-value. There were 1,000 t-tests, thus there were 1,000 p-values. Now here, with a sample size of 5 per group, we see a distribution of p-values. This distribution is roughly uniform. If there were a billion p-values that I had simulated, then this distribution would look very, very close to rectangular. And that means that every p-value under a true null hypothesis in statistical theory has an equal chance of appearing for any t-test. Okay. In this case, I'm interested in the p-values that are in the 5th percentile. Okay, I've labeled this with the dashed line, and this is my alpha level. This is my level of statistical significance. So what I'm saying is any p-value that is less than 0.05, I'm going to declare it as statistically significant. In my case here, I have 44 of them. 44 out of 1,000. Well, that's similar or the same as 4.4 out of 100. In other words, I found 4.4% of my p-values to be statistically significant under a true null hypothesis with a sample size of 5. Now, what happens with a sample size of 30? I found 5.6%. What about 100? 4.2%. What about 500? 4.7%, and so forth. The point here is that these are also sampling distribution of p-values. However, they do not converge on any value in the population. They are uniformly distributed. Hence, any p-value anywhere between 0 and 1, but not including 0 and 1, has an equal chance of occurring under a true null hypothesis. And 5% of them, Fisher declared these will be considered as statistically significant. Now, let's take a look at the distribution of effect sizes. Hohn's effect size D. Here, with sample size of 5 per group, what you see are many effect sizes that are not equal to 0, much bigger than 0. Cohn declared that any effect size between negative zero point 0.2 and positive zero point 0.2 are considered trivial, irrelevant effect sizes, are not substantively significant. Anything greater than zero point 0.2 or greater than negative zero point 0.2, these will be considered substantively significant. And the p-value, pick up on the largest effect sizes. So there's roughly about 5% of these are statistically significant, large effect sizes. But remember, this is all under a true null hypothesis. Remember, Cohn's D in the population is equal to 0. All of these are false effect sizes. They all should be clustered right at 0. However, that is what sampling theory is about. That is what's known as random sampling error. Every time you take a sample, you can predict that it will not produce exactly the same results as before. So statistical theory allows us to make some kind of statement about what is likely or unlikely to happen under random sampling. And we see as increasing sample size is in fact useful. As you increase the sample size to 30 per group, there are more trivial effect sizes, more of the realistic effect sizes under a true null with Cohn's population d equal to 0, but still there are some that are false effect sizes, false substantively significant effects still appearing with n is equal to 30 per group. There's fewer with n is equal to 500, even fewer with n is equal to 500. But here, there is trivial effect sizes starting to be picked up as being statistically significant, although one of these was greater than -2, so there was also a statistically significant, but presumably substantively significant effect size. But let's take a look and see what happened with n equals 1,000 per group. Now there are no more substantively significant effect sizes according to Cohn's criteria, and all of them are trivial effect sizes. However, statistical significance continues to pick up the values in the tails of the distribution as being statistically significant. Here, I've created bar graphs, which is the same sampling distributions as you saw before, but now they've been categorized into the four distinct groups. So we have 206, 250 trivial effect sizes, and the rest are either small, medium, and large. And what you see, what you saw in the distribution right there, there's a certain proportion of them that are statistically significant. As sample size increases, they start to disappear, the large effect sizes, and now medium effect sizes are starting to be statistically significant. And as sample size increases to 100, only small effect sizes and trivial effect sizes are present, and a proportion of them are statistically significant. Finally, with n is equal to 500, only one small effect size was picked up, and the rest were trivial. 999 were trivial out of 1,000. And then when you get to a sample size of 1,000, all of them were trivial effect sizes, which is the same graphic as up here. And there's a certain proportion, though, that are statistically significant. So let's consider the actual numbers that correspond to this picture. I'll go back to the n is equal to 5. We can focus on that. This says that 250 are trivial effect sizes, so they're not statistically significant, and they're not Cohn's effect sizes according to his criteria. So there are 250 of them. The remaining 313, 216, and 221 add up to 750. Okay? Of these 750, 44 are statistically significant. Okay. So, as I showed you earlier with the p-value distributions, I have 4.4% of the p-values statistically significant, almost 5%. However, consider this, that statistical significance has picked up 44 out of 750 that would potentially be interpretable as meaningful in some way. And 44 out of 750, that amounts to about 6%. So statistical significance has allowed us to disregard much nonsense when it comes to something that occurs under a true null hypothesis. Now, consider the n is equal to 1,000 per group result. This bar graph. Okay, there are no substantively significant Cohn's effect sizes here. So there are 932 that are not. However, there are statistically significant effect sizes. There's 68 of them here. Well, that's zero statistically significant effect sizes that correspond to anything substantively significant. So statistical significance is not helping you pick up anything meaningful anymore. And at that point, we have to consider, what does this mean if you're going to pick up an effect size with, let's say, n is equal to 1,000 per group, and it's going to be larger than something that's trivial. It's going to be substantive. You don't really need statistical significance in this case. This is where statistical significance is losing its utility as a good screening tool with small sample sizes. Now you have to apply some other reasoning. What would make such a substantively large effect size appear when you have such a large sample size? There you're pursuing something scientifically perhaps quite meaningful and useful. But that's beyond what a statistician can provide as far as interpreting or helping you decide whether this is truly meaningful. And if you see in the program, it does produce these data that were used to populate the table with Excel. That is 250, 706, 44. You see 250, 706, 44. And then I did some post processing with this Excel to get some of the percentages calculated. All right, now let's move on to the false null hypothesis, which when I first wrote this paper, the reviewers would ask, well, okay, fine, true null hypothesis, but what happens under a false null hypothesis? Well, I showed you how the false null hypothesis was created. It was with the sim false null simulation, where I added 20 points to the mean for the experimental group, and the population effect size then became zero point 0.8. But I'm still testing the null hypothesis that the mean difference is equal to zero. And what I find in this, with n is equal to 5 per group, that I have no longer a uniform distribution, but a right skewed distribution, where the majority, the prevalent p-value is in the fifth percentile. Okay, this is I see 199 p-values in the fifth percentile. In other words, 199 of these are statistically significant compared to what I showed you under the true null hypothesis, which was only 4.4%. Well, what is this 199? Well, consider 199. Well, let's bump it up to 200. Makes the math arithmetic in the mind easier. So 200 over 1,000, that is the same as 20 divided by 100. That is the same as 1 divided by 5. That is the same as 0.20, and that is the same as 20%. So now I'm picking up 20% of the p-values as statistically significant compared to 4.4% under the true null hypothesis. So there is now a chance to find statistical significance if that is better than what you get under a true null hypothesis, which is good. And does this improve as you increase sample size? Yes, it does. In fact, it improves all the way to, let's take a look at n is equal to 64. Okay? Because beyond that, everything is in the fifth percentile. All the p-values are in the, you have essentially 100% power, so it's not an interesting graphic. But here, I think this makes the point. Okay? Most of these p-values, in fact, 992 out of 1,000 are in the fifth percentile. Those are all statistically significant p-values under a false null hypothesis. And this means that I have 99.2% of the p-values are statistically significant. Now that might remind you of a power calculation, and it should, because that's exactly what this is. And to demonstrate that point, I'd show you a graph from G Power, where I went ahead and ran a powered for a two-sample t-test. I looked for an effect size equal to zero point 0.8, large effect size. My level of statistical significance, alpha, was 0.05. Sample size in each group is 64. I calculate and I find G power tells me that I have 99.4% power to detect such an effect size with 126 degrees of freedom or 64 observations per group. 128 total minus 2 is 126 degrees of freedom. So I think this is the main point that I want to leave you with. So, in summary, let me go back to the table 2, and state following a few things. First, you can never prove a null hypothesis is true or false. You will never know this. The best you can say is that it's unlikely that the null hypothesis is true. Now, how is unlikely defined? Unlikely is defined by your level of statistical significance. I'm using a 5 percentile value here, 0.05. Okay? You can use whatever value you like to decide what is unlikely for you, but you need to have some sort of cutoff. Otherwise, as I'm showing you with these data, you will be pursuing a lot of nonsense. Statistical significance under a true null hypothesis allows you to forego, allows you to eliminate a lot of nonsense. As I showed you, with n is equal to 5 per group, 750 out of 1,000 were substantively significant. Okay, that is 75%. Statistical significance reduced that load to 6%. So, okay, these are also false effect sizes because I know the population Cohen's d is equal to 0. So these are, in fact, overestimates. However, at least you're pursuing a few of them and not 75% of them claiming all sorts of things about substantive significance. The situation improves with increase in sample size. So with n of 30, which is a fairly decent sample size between two groups, for two groups, it's a total sample size of 60, you have almost half of them were considered substantively significant if you have no other criteria to go by except Cohen's criteria. Whereas if you also apply statistical significance in your considerations, you reduce this number down to 12.5%. As the sample size continues to increase, for instance, with n is equal to 500 per group, now under the true null hypothesis, where Cohen's d, population d, is equal to 0, one of them popped up as being something meaningful, substantive. It's actually a small effect size, but the point is, it was statistically significant. So statistical significance still picked it up. Whereas when you finally get down to n is equal to 1,000 per group, the total sample size of 2,000, 68 of them were statistically significant, but none of them were substantively significant. So what I'm saying at this point, statistical significance has lost its utility as a viable screening tool for effect sizes, for differences in means. And not having statistical significance, though, when you have smaller sample sizes, is a real harm to scientific research. I don't know how else to convey this idea to you except to please run your own data, do your own analyses, consider the results, and consider what it means when you don't have statistical significance to help guide your thinking about something that's meaningful. Okay? When you have more than 1,000 per group, well, then, if you find a large effect size, under a true null hypothesis, this would be truly an unusual result. I'm not even care about the p-value. I would be looking at this and thinking there must be something meaningful going on. Yes, it requires replication. Redo the study. But you are pursuing something meaningful, and statistical significance is not going to help you at all in this case. So it stopped losing its value at that point. But you must remember, statistical significance was created over 125 years ago. Why? In order to deal with small sample size research. It was designed for small sample sizes. And to ban statistical significance is to say I'm banning small sample size research, which I believe is clearly nonsense. All right, so thank you for attending this video lecture, and I hope to see you again. I plan to do another video on the statistical significance of Pearson correlation coefficients, which is another paper I have as a preprint on chaos, but I want to publish that paper as well, and I will do another video as a result. Okay, so till then, bye for now. Thanks for listening.